Now let's see an example of a composition of a function and the calculation of its domain, which is a little bit more sophisticated than the other examples. For that, let us start with the following functions. The function f, whose domain is from -1 up to 2, and which maps these numbers into real numbers. But for the present case, I'm going to immediately set the codomain as the range of the function. And the range in this case is from all the numbers from 0 up to 4. The function in question will map the x numbers in this interval into f of x, but f of x is just an abbreviation for x squared. So this is a simple example of our parabola, but just a section of it, the section between -1 and 2. For the second function, consider g, which maps from 0 up to 2 into -1 up to 1, and every y is going to be mapped into g of y, and g of y is the same thing as y minus 1. Now, the composition we'll be interested in this example is going to be g of f. We're going to analyze it in detail, and we are also going to leave the f of g as a homework. Focusing on the g of f, let's first try to compute the thing. G of f, well, is a function that acts when acting on x, is going to give us, by definition, g of f of x. But what is f of x? F of x is just a symbol for a number, in particular x squared. So we can substitute here the x squared. So we have g of x squared. Now we know, in general, how does g acts on the y, but if that y is in particular that number of the form x squared, then we get not g y minus 1, but g of y x squared is x squared minus 1. So this thing is x squared minus 1. Now, what is the domain of such a function, of these composite functions? Well, let's see. By definition, as we saw previously, on the previous video, we know that the domain of g of f must be all those x's that live in the domain of f, as long as their images, meaning f of x, belong into the domain of g. Let me just say it again. It's all those x's in the domain of the first function, the f function, whose images lives in the domain of the second function, which in this case is just the g function. Explicitly, now let's make explicit these two statements. So the domain of f, it's here. So we want those x's that belong to -1 up to 2. Now f of x squared is just x squared, and the domain of g is here from 0 to 2. So this must belong to 0 and 2. Now you have just to do this calculation, the calculation of the elements in this set. Before we make such a calculation, let's simplify the statements that are involved, meaning this statement and this statement here. This statement here can be simplified because it essentially says, well, that x belongs to this set, but to say that is the same thing as saying that x is between -1 and 2, excluding the 1. So this is less or equal because it includes the 2. This is just less because it does not include the -1. To simplify this situation here, this statement, well, is analogous to this one. So it just says that x squared must be between 0 and must be less or equal than 2. Now let's go further and simplify this second statement here. And usually, when we deal with functions with x squared, it's useful to draw a graph for it. So let's make a picture that encapsulates these three things in this statement. So the first thing that we have to show graphically is what is x squared. So let me draw you the function x squared. The function x squared is like this. It's a parabola that contains the origin. So along the horizontal axis we find x. On the vertical axis leaves x squared. Now, this part here is already done. The x squared, we already have a picture for it. But let's now draw the picture for the other two. This 2 here is an upper bound for the y values. So the set of points in the plane which have always y equals 2 is like this. So this line is all the points in the plane whose y coordinate is always 2. On the other hand, all those values which has y coordinate equal to 0, well, is the following dashed line. Is dashed because you want x squared not equal to 0. That's why. Now what we seek is all those x's that make x squared have at most 2 and as a minimum 0. So that is bounded in this interval. Looking closely at the picture, I think it's evident what is those x's. It's all is from minus square root of 2, because minus square root of 2 squared is 2. So this x here is mapped into this value here. On the other extreme, we find the square root of 2, which is mapped into 2 here. All those values between minus square root of 2 and square root of 2 are always mapped between 0 and 2. The only thing that is left is to exclude the x equals 0, because x equals 0 is mapped into 0. So the simplification of this statement is in turn, well, let me draw this arrow, is all those x's which are between minus square root of 2 and square root of 2, and x is different from 0. So we have now just simplified as most as we can the original statement here. Now with this thing simplified as this and this thing simplified as that, we can now easily compute what are the x's that live in this set here, meaning the x's that live in the domain. So let's see. Let's draw now a picture for our x's here. So let me draw an horizontal line here. On this horizontal line lives all the x's, so let me draw the first set. But before I do that, let me just draw the key points. For example, the 0, minus 1, 2, and the square roots. So here is 0, here is minus 1, minus 2, here is 1, here it is 2. The square root of 2 is about 1.4, so let's make it like this. It's about here. Square root of 2, and minus square root of 2 is somewhere here. Now let me draw each one of these sets. The first one is between minus 1 and 2. So minus 1, it's here. It's open, and now the set contains all the x's up to 2 here, including the 2. So it's closed here. For the second set here, let's draw it. So it's from, includes the minus square root of 2, so it's closed. It goes up to the square root of 2, it is closed. However, it is open here at the 0. So what we seek here, essentially, to do this calculation, to calculate the x's that enter this set, in this set, are the x's that satisfies this statement and this statement simultaneously, meaning it is the intersection of these two sets here. But we can solve this graphically. It's quite easy. So the final answer is going to be, so the domain of g of f must be all the x's that goes from minus 1 up to the square root of 2, excluding the 0 and the minus 1. So from minus 1 up to the square root of 2, excluding the 0. And that's the final answer for our problem. Before we finish this example, I would like you to see this example from the diagrammatic point of view. We already seen this in our original example of a composite function, so let's now focus on that right now. So let's construct a diagram that essentially translates all the calculations which are involved. And for that, let me draw the mappings which are involved in these functions, in the composition in these functions and in the composition of these functions. So let's do it in 2 steps. The first, to note that the composition g of f essentially does the following. So we start with an x. F is a first function to act on x, giving us x squared, and then g acts and gives us x squared minus 1. So this is a basic diagram. All these elements here have their own sets in which they live. So I want now to make a diagram to represent that. So the diagrammatic representation of this composition is as follows. Let me draw here 3 lines which is going to represent the sets in which these variables live. So recall, for example, that our x, where does it live? Well, x lives in the domain of f. But what is the domain of f? Well, the domain of f is from -1 up to 2. So let's draw it. So let me draw it. So it's 0 here. This is -1. This is 1, and this is 2. So the set which is involved is open here up to closed here. So this is the domain of our function f. Now, what is the range? That's why I gave you the range from the start. It's 0 to 4. Let me draw it then. So it's the 0 here, it's 2 here, and it's 4 here. So it's closed here, and it includes all the outputs up to 4. So in conclusion, x lives here, somewhere in this set. It belongs to the domain. And now f maps it into some value in this interval. And that value is the form x squared. Now let's repeat the same idea, but for our second function, the g function. So the y lives between 0 and 2, excluding the 0. So let me draw it from 0 open, from 0 up to 2. This is the domain of g. And now let me draw the range. The range is from -1 up to 1. So let's draw it. So is 0 here. This is -1 up to 1, somewhere here. So in this case, it's open and then closed. And this is the range of g. And in particular, what does g does? Well, it maps those values in this green interval into elements here in this interval. Now, from this diagrammatic point of view, what does it mean, the calculation of the domain of the composite function that we have just done? First, recall the domain here. It's done here, so let's represent it from -1 up to the square root of 2, excluding the 0. So from the -1 open, excluding the 0, so it's open again, up to the square root of 2 here. So here we find the domain of g of f. Now, let's see what does it mean, the domain. From the original definition, what do we want? We want all those x's in the domain such that the images are in the domain of g. In other words, we want all those x's living in this set, the red one, such that their images, the x squared, lives in the domain of g. So the function f maps all these set elements here into this red one, but there are some x's here that are mapped instead just into this subset. We want to find those. And those x's that are mapped into the green set are exactly those that are in this blue set, from -1 up to the square root of 2. Can you see? In other words, the image, let's see, the image of the blue set is the green set. In fact, let me just rephrase this in another way. Because in seeking those x's in the blue set, in seeking those x's such that the image falls in the green set is just a particular example of what is a preimage of a set. In other words, the preimage of the domain of G under the f function is exactly this thing here. Let me write it explicitly. F minus 1 of what? Of the domain of G. Can you see? So the preimage, so the x's that are mapped into the domain of G are exactly the domain of G of f. In other words, the elements in the domain of f are just like the fruits in your local supermarket. Now, the elements between 0 and 4 here are all the labels that we can use to attach to our fruits. Now let us choose our favorite labels, those in the domain of G. And we ask, what are the fruits? What are the x's here that are mapped into those labels? Well, it turns out that the fruits are exactly from minus 1 up to the square root of 2, excluding the 0 and minus 1. In other words, those are the preimage of the domain of G. Okay? Gives us the fruits here that are attached to those labels. Well, this is a wonderful observation that we have here, a very important calculation, and a one that will appear many times. Now,